Okay, we're going to see if we can take a look at the visual representation of probability. I know this is supposed to be mostly using Excel, but I think it's sometimes useful to actually take a look at the picture. What I'm going to do is draw what's referred to as a Venn diagram. A Venn diagram is just a visual representation of the sample space. Now, that means that all observations are inside this square circle, square thing here, so that we can represent events as, say, circles on the sample space. So this might be, for instance, event that I could label event A. Now, event A might or might not overlap with any other events. If they're mutually exclusive, there's no overlap like the picture I have here. However, if I am looking at having them overlap, say I put on yet another event like that, I can have them overlap, and I'll call this one that overlaps event B. Now, notice when I'm looking at event A and event B, they are not mutually exclusive, meaning they overlap, and the place where they overlap looks like sort of this little football here. Well, that football, let me see if I can get that into some color here for you. If I can make that thing into a color, maybe we'll turn it red. This little area in here is the intersection. Okay, that wasn't the best coloring I've ever done, but there it is. That's the intersection of events. Now, that's the intersection. The union is when all three pictures, all three pieces are together. For instance, if I am looking at an intersection, I've got just the football. But if I'm going to look at the union, it's everything in A plus everything in B. But if all I did was add up A and B, then I actually have double counted the football, which is where you get that formula in the book, probability of A plus the probability of B minus the intersection is what gets you the union. Okay, so that's the union. But now, what if I want to do something a little bit more interesting? For instance, let's say that what I want to do is I want to start dealing with looking at something I call the theorem of total probability. Your book doesn't actually name that in particular, but to do that, I'd like to point out that you can either do events like we had with circles, or we could do events by partitioning the entire sample space. For instance, I could call everything to the left here A, and everything to the right then becomes not A. Well, all right, so A, and I could call that little c for not C, or it's the complement of A. Sorry, not C, but it's the complement to A. So it's everything that's not in A is on this side. Everything that's in A is in this side. Okay, so we can do it that way. Well, that's well and good, but let's clean that up for a minute. Now what I want to do is I want to think about my sample space as being divided into these two groups. And for the sake of argument, how about I let these be called, say, again, I'll label this one A, I'll label this one not A. And then what I'll do is I'll put another event on top of this. This event on top of this thing, I can call event B. Now, notice that event B here at some point actually has this little tiny intersection with A. So I can show you that. I'll actually see if I can give that one a little bit of color here. And we'll see that that blue colored area is the intersection of A and B. Okay, well, the intersection of B with not A is what's left over inside this circle. I could color that, say, yellow, and there we have it. Now, what the theorem of total probability does is it goes after the idea of what happens if you want the area of B. So what happens if I want the area of B? Well, if I want the area of B, and I'm looking for the probability of B, whoops, let's get that into a color we can read. If I want that probability of B, I can either try going directly, using the counting rule or something else to find its probability, or I can notice that it's made up of those two parts. Those two parts have names. The blue part is the probability of B intersected with A, and the yellow part is the probability of B intersected with not A. So the theorem of total probability just tells me that anytime I'm looking for the probability of an entity, I can add up the pieces. Now, it is often useful to realize that, and that has become what's called the theorem. Let me clean that up. It's become the theorem of total probability. Oh, that didn't come out nicely at all. It's called the theorem of total probability. Okay, so that ought to about do it.